So now that you've seen how to integrate a triple integral over a nice rectangular solid, we're going to get to introduce how to integrate over general regions. And like the two-dimensional case, we're going to define the boundaries of the regions for the very first variables we're going to integrate over as functions of the other variables. Since there are three independent variables, the very first integral that you'd integrate over, in this case z, should be boundary functions based on x and y, x and y. Because we're thinking about z, the z direction is the top and bottom direction, we can think about the boundary integrals as the function below and the function above. In this graph, we have a bounded region, the region E, which is inside this acorn-looking shape. If you look at this acorn-looking shape, the top part is pretty clearly the red the red surface over here, and the bottom part is pretty clearly this orange bottom part, that's the bottom part of the acorn. So the general surface that describes the top is this square root surface over here, which is basically the upper hemisphere of a sphere. So it's the sphere equation, and then we just took the square root, so we get the upper hemisphere. We just want a region of this part of the sphere that cuts into the bottom parabola curve. So this orange curve is actually a surface, isn't actually a sort of parabolic surface. If I click on this, you have to see the general version. And I can overlap the two complete regions to see how we got the boundary curves. The second important part of the notation for this kind of region is not just the upper boundary and the lower boundary of the surfaces, if you choose z to be your first component. After that, you have this region D. This region D is supposed to be just like our type 1 or type 2 region inside a plane. We use exactly the same techniques to describe this region as we did in the double integral general region examples. The real difficulty is finding this projection into the xy plane of the solid region. Let's take a look at an example. In this example, we'll practice describing the solid region E in a series of inequalities as above from the description given to us in the problem. The region E is described as the bounded region cut off from three-dimensional space with two surfaces above the xy plane. Our first step to visualize this process is to graph it in a tool like GeoGebra or any other 3D graphing tool that you might have. We start by graphing one of the surfaces, which happens to be the sphere. Next, we enter in the graph for the parabolic shape. You can now visually see these two surfaces cut off a bounded solid region between them above the xy plane. In particular, the solid region is trapped above the parabola below the sphere. If I remove the sphere briefly, you can see that that region we're thinking about is somewhere inside that parabola above it, and it's somewhere below the sphere right over here. Therefore, our top surface is the sphere equation, and our bottom surface is the parabola equation. We want to describe that as an inequality with equations, so we find the equation for the top surface over here, which is the sphere equation, and we just algebraically solve for it in terms of z, because we're trying to find the top in terms of z. And then we do the same thing for the bottom surface, that is this quadratic surface, paraboloid surface over here, which is already in the right form because you already have a z here. You just know that you want to be above that surface, so you just make your z greater than or equal to. That will be your lower limit of the first integrand. The next step is to try to find that projection into the xy plane, because after you eliminate the z variable, you want to know, okay, what are your restrictions on your xy variables as they relate to each other inside this region. And so the first step to doing that is figuring out where's the intersection of these two surfaces and how to describe that in terms of just x and y. You can see the intersection is this circle-looking picture over here. Generally, a strategy that works pretty well in terms of figuring out the intersection of two surfaces is to take a single variable and set them equal to each other. In this case, we already found the equations of each surfaces in terms of z, so we just take their equations of z and set them equal to each other. In this case, that would be this crazy square root thing with a minus x squared and a minus y squared equals this square of x plus square of y plus 1 on either side. Notice algebraically we try to solve this the ones would cancel out, but you still got the square root and a not square root here and two variables. It just so happens from the picture this looks like a circle anyways. And also, whenever you have a structure of an x squared plus a y squared or an x squared minus a y squared, that is the structure of a circle variable. You should think polar coordinates centered at the origin. In which case, we could just describe our x squared plus y squared as just a third variable, r squared, that radius of the circle. If we do that substitution, we kind of simplify, at least a bit, this equation. So I just see my x squared and my minus x squared minus y squared in this equation and just replace it with a minus r squared. I see my x squared plus a y squared in this equation and replace it with just an r squared. Now I have my z's that I set equal to each other like I would have done anyways. And I tried to solve this equation. Sorry, that's supposed to be an r squared, not a 6. I'll fix it. So if this was an r squared, so I've fixed it now, you can see that r squared is over here, and you want to algebraically solve this, which basically boils down, for r, which basically boils down to subtracting the 1 from both sides, and then using the square to get rid of the square root on the left, so you'd have 16 minus r squared equals r to the 4th. You can move all your coefficients to one side, it becomes a generalized quadratic expression. You can use the quadratic formula. And then you get a couple square roots because you're actually solving for r squared when you first use quadratic formula. You use the square root again to get rid of the r squared, which in this case gives you only two solutions, two real solutions. And so you either have a negative radius, which doesn't make sense for us, or a positive radius, which is just some crazy number over here. I'm mostly going to reference this number with a positive radius with R2 just to save space, but it really is a numerical number that you can approximate with a decimal number that you can substitute into this equation everywhere you see R2. Now that we know what radius circle satisfies this intersection for x and y, we could just describe x and y, that relationship, as an equation for a circle with this particular radius that we solved for. This becomes the boundary curve for the disk in D. Visually, we can project this circle of intersection just in the xy plane. And if I restrict my choice of x and y's to plug into my top function and my bottom function so they're only inside this disk, well, the part of the sphere that I get, if I only restrict to x and y ordered pairs inside this disk inside the xy plane, it actually happens to be just this top of surface that I'm looking for my solid region. And doing the same for my bottom parabola gives me this orange sphere surface down here. You can more clearly see the solid surface now that I took out or restrict myself to just sticking to xy ordered pairs that give me points inside the region I'm concerned about, and ignore the xy ordered pairs that don't. How I got this, once again, is I find the intersection curve of the two surfaces and just use that to describe only my x and y coordinates. That's the circle over here. I forget my z coordinate, it goes away, and that gives me a copy of this circle down here. Then I recognize if I choose points within this circle, that's going to be inside the domain. That gives me the solid region over here. If I choose points outside of the circle, that gives me points outside of the region. In terms of algebraic functions that we're solving for, that projection disk is our region, our type 1 region from the double integral definition. What we do is we take our equation for that boundary curve and we just try to describe it so that it is a function of y by solving for y. If you do this, you get the lower half of the circle in the xy plane, which is the negative of the square root. And then you also get a second equation for the upper half of the circle, which is the positive square root version. The last variable that you have to bound is going to be just the x. It cannot be more negative than the negative of the radius, and x cannot be larger than the positive of the radius of that circle. Now that we've described each of our variables in terms of inequalities, we get to write them down collectively to describe the region. So we're looking for all x, y, and z coordinates so that the x coordinates are bounded between the negative and the positive of the radius that we calculated over here. The y coordinate is going to be between the negative square root for the equation of the circle and the positive square root for this equation of the circle. That's the bigger version. And the z-coordinate is going to be the bottom surface, so it's got to be larger than the bottom surface and smaller than the top surface.